So maybe that has something to do with it as well.
So just to be clear, Delta does not appear to be more virulent, in other words, more serious in kids, and serious disease is rarer than in adults, but they're seeing high numbers because the COVID outbreak is so large. Ritu Banerjee is Associate Professor of Pediatric Infectious Diseases at Vanderbilt Children's Hospital in Nashville, Tennessee. Today we bring you another interview in our regular series on substance use. Many parents have angst about the pressures their teenagers will face to try cannabis, alcohol and other illicit drugs. But what puts some kids more at risk of becoming a regular user while others are able to avoid substance use? It turns out the answer might, partly at least, lie within the brain. Jennifer Debenham is a researcher with the Matilda Centre for Research in Mental Health and Substance Use.
I'd probably preface this by saying you can't look inside someone's brain and determine whether they're going to use drugs or not. We really talk in terms of risk and probability. So there are other environmental and social factors at play as well. But a recent review of the literature found that there are limited neural predictors of single-time substance use. However, for more frequent use, there are some associations. There are some neural associations with more frequent substance use. So specifically, we found that white matter integrity, so this is kind of a measure of the efficiency of neural messaging.
Just to explain, white matter is, if you like, the cabling of the brain.
Yeah, exactly. So we're looking at the cabling of the brain between the frontal cortex, so that's the front of the brain, and the limbic system, which is kind of towards the middle and deep inside the brain.
And the frontal part of the brain is where we've got what's called executive function. This is where we can control our behaviour, control what we say, and also plan how we're going to do things in the future.
That's exactly right.
And the limbic's more basic than that.
That's exactly right. So the limbic is more emotion and memory.
What are the features of the cabling that may say, well, this person's more at risk or maybe more destined to use drugs?
So it's tricky. So it's white matter integrity, which is essentially a measure of the insulation around a neuron. So around neurons, you've got this fatty tissue of myelin, and that strengthens neural connections, and it strengthens the speed at which messages are sent. So we find that the connectivity of these tracks between the frontal part of the brain and the limbic system play a role in risk-taking. So reduced white matter integrity is associated with risk-taking and also substance use during adolescence.
But isn't that what adolescence is? And therefore, how do you differentiate it from normal adolescence? Because normal adolescents like taking risks.
Well, exactly. But these are in samples where we're comparing across the board all adolescents, and everyone develops at different rates. But there are particular trajectories of neurodevelopment which have, say, reduced white matter integrity. And that's more highly associated with substance use.
So what you've said there is that, in some young people, there is this cabling issue from the front of the brain through to the limbic system, the basic emotional part of the brain. Let's go upstream from that. Is there anything that predicts why the cabling problem occurs in the first place?
That's a great question, and hopefully a question we can answer with the ABCD study, which is currently tracking young people from age 10 all the way up for about 10 years, and they're going to look at what typical trajectories of neurodevelopment look like, and then what kind of atypical developmental pathways look like. Because currently we don't quite have this window of normal. There's so many different tracks here. So in terms of what might promote more negative developmental pathways, it's not exactly within my research area, but from other research, it's things such as the upstream determinants of health is kind of what you would go into there, which is such adverse childhood experiences and the like.
Now, in the past, we've done quite a few stories on this on the health report, and what we've spoken about is research, particularly from Melbourne, which looks at early use of alcohol, cannabis and other drugs. And talking about this cabling is that the process of growing up is like pruning a rose bush, is that you've got this overgrown brain when you hit adolescence, and then that gets pruned, in fact, as you grow up. And what happens is that the pruning goes wrong, and this cabling does not necessarily go in the right direction, and it can be molded to actually not just produce harm, but a permanent sort of dependence or, if you like, predilection for drug use. Have you found the same sort of thing?
Well, so you're definitely on the money there. So this pruning process is, allows for leaner, meaner, and more efficient brain activity. And at some stage it can go wrong. Maybe you have a delayed neurodevelopment which increases your propensity to use substances, or maybe as a result of substance use you get this a change in the cabling. But I would be reluctant to say that, that this always tracks into adulthood, because what we're speaking about here is neuroplasticity. And this is the brain's inherent ability to change. And it's this pliability, this malleability, which is really characteristic of adolescence and young adulthood. And this neuroplasticity offers both the opportunity to grow and to change and to repair, but also this the risk to damage. And it does mean the brain is more vulnerable to damage. But exactly how long this damage may last is still unclear. The jury's still out on that one.
Jennifer Debenham is a researcher with the Matilda Centre for Research in Mental Health and Substance Use. Well, Tegan, quite a few fascinating stories there with COVID. I mean, Alan Saul was, I thought, devastating, actually.
Yeah, the doubling rate stuff is a bit sobering. I'm not really sure what we do with that information.
Yeah, and it wasn't as if he was criticising the Doherty model. He was just saying that we're all misreading it.
Yeah, I suppose more will come out in the coming days. But for now, Norman, it's time to answer some questions from our audience. They've been writing into our mailbag, which, of course, you can write to yourself at healthreport@abc.net.au.
So let's go.
So John has written in, Doc, and asking, he has had spasmodic atrial fibrillation and had a transient ischemic attack or mini stroke about a year ago. He was put on meds to reduce the blood clotting, and interestingly, he's found that the fibrillation has also stopped. Is this common?
So just to translate a bit about that, atrial fibrillation is an irregular heartbeat. And what happens, just to give you a little bit of the anatomy here or the physiology, is that there are 4 chambers in your heart. The 2 top chambers are the atria, and that's where the blood comes into your body on the right-hand side. From the deoxygenated blood comes in on the right side and then goes into the right ventricle, so the ventricles are the other 2 chambers. Then that pumps, it's much more powerful, and pumps the blood through the lungs to pick up oxygen. Then it goes into the left atrium and then into the left ventricle to be pumped out to the rest of the body. Now the atria, particularly the left atrium, the atria also have a very other important role, which is to control the rhythm of the heart. So the electrical conduction is controlled from there. So the atria, if they were allowed to beat by themselves, they'd beat at a very fast rate. And there's, if you like, an electrical break in the heart, which then transmits a much more regular message to the ventricles to beat. And an atrial fibrillation is when that electrical communication is abnormal. And what sometimes happens, or what seems to happen, is that the nerves around the